So last time we learned what's the, how you can use the expectation to show the existence of certain combinatorial object. So you define certain random variable x, and then you compute the expectation, and let's say this is alpha. Then you know that there is it is possible to have this at least alpha or at least, at most alpha. And this x is not just any random variable, but it's linked with some combinatorial object. So this actually shows the existence of certain combinatorial object. And we learned about one example by showing that if you have a graph G, you randomly distributed vertices over to two parts, then probability that an edge is actually crossing here, not like, not both of them are on the same part. This is a probability half event. So that if we let the x to be the number of these crossing edges, then we can actually compute this by using the linearity of expectation, where this xe is indicator random variable regarding whether the edge is crossing or not. And this is actually half times m, where m is the number of edges. And that shows the, an answer on the max cut problem that we run this theorem that every mh graph G has a bipartite graph. With at least m over two edges. And this is almost tight because if you consider a complete graph, Kn has n choose two edges, and you can actually check that the maximum number of edges in any bipartite subgraph is n squared over 4. Cannot be more than n squared over 4. So this is best possible. But this is roughly, half of m plus small o of m. So you cannot really improve this much, but this suggests that maybe we can add something more here, which is some linear term. And indeed, Edwards show that you can actually improve this a bit more. So if we have a graph with m edges, then G contains a bipartite subgraph. Or we can just say it has a max cut, which is L size at least this number, m over 2 plus negative 1 plus square root of 8m plus 1 over 8 edges. So here, this is, roughly square root of m. And if you actually compute the formula, so we can actually, for the complete graph, you can actually let n choose to be m, and then you find the max cut, and there the formula is in terms of n, but you can convert it to a formula in terms of m. Then you actually get this number depending on the parity of n. If n is odd, then I think you get this, and if n is even, then the number you might get plus 1 here. But that shows that this theorem is best possible. for complete graph, I mean, you cannot have more edge than this. So this is as best as possible. So let's consider the proof of this. You can divide this into two cases, but let's just consider the one case. And I will leave the other case to an exercise to you. Assume that this chromatic number of G is 2t plus 1, so odd number. When it is even, then you can do in a similar way, but the computation is slightly different, so let's just assume that this is the case. And what's now what we want to do? We want to change the random process a bit. So before, how did we do that? We have several vertices in a graph. Then for each vertex B, we either put it in A or B at random. And for U, also at random, W, X, we put them all independently, uniformly at random. So that the probability that both of them are in here is actually half. But can we somehow modify this process so that the probability of probability of this edge being a crossing edge is slightly above half? So we can actually do that by using this chromatic number. So if we know a graph G is, say, this is 2t plus 1 colorable, what it means is that you have a vertex partition so that all the edges are already crossing here. And there are no edges inside here. These are all independent sets. So now what we want to do is we want to put these vertices into either A or B. And then we want the edges here is likely to be the crossing edges. One thing is that here there are no edges between these pairs inside of this independent set. So if we somehow guarantee that they all go together, either they all go to A or either they all go to B, then it's likely that these non-adjacent pairs are again non-adjacent here. Then we can, expect that to boost up the probability of these other pairs to be crossing rather than non-crossing. So these are sure to be non-crossing if we put all of them into either A or B. So these are less likely to be crossing. So out of all pairs, the probability that they are crossing or not, if you sum them up, then they should be, constant. So if these pairs becomes more likely to be non-crossing, then the other pairs probably become more likely to be crossing. So this motivates us to, find the following random procedure. Let V1 to be 2t plus 1 be a partition of it, of the vertices of G into 2t plus 1 independent set. And how we make a decision is that for entire V1, we flip a coin and then put them entirely in A or entirely in B with the probability half. And independently with that, V2, we either put entirely in A or B by flipping a coin. And V3, we also do that. And formally, we can write this in several ways, but we can actually choose I. Okay, so what I said, okay, let's correct what I say. Instead of doing this, I think the other way is more easier to compute, and it is better to compute. No, let me correct myself. So that's one possible way of thinking. But another way is that we can, if there are four things, let's say, P4. So let's say there are like 4 parts. And then for each of them, you can either choose to put, one in here or the other here, and one in here or the other here, independently at random. Then we get a partition. That's one way. But in that way, there is some possibility that these are not balanced. So many things are here and small things are here. And in general, if these are balanced, then there are more chance to get more crossing edges. But unbalanced, you are likely to get less crossing edges. So instead of doing that, what we can consider is that we randomly choose exactly 2 sets here and then put here and the other one here. Then this random procedure actually guarantees that these are somewhat balanced. That also gives you a slightly boost on a probability that a given edge is crossing. So we use these 2 ideas. One idea is that we put all the things in this independent set to either A or B to boost up the probability of edge being crossing. And also, instead of, random, independently random, we choose, each one of them to, A or B. Instead of that, we can actually specify the number of objects that we will put into A and we will put into B. So 2 here or 2 here. Or if there are an odd number of them, then 3 here and then 2 here. So formally, what we do is we choose I out of the index set between 1 and 2t plus 1 with size t uniformly at random. Meaning that there are 2t plus 1 choose t many possible sets of size t lying inside of 2t plus 1 bracket. And out of that, we choose 1 so that each set is likely to be chosen with the probability 1 over 2t plus 1 choose 2t. And we let A be the union of Vi, where I is in this randomly chosen set I, and V is the remaining vertex set. And let X be the number of crossing edges with respect to the partition A union B. Then, what's the probability? So for E, which is between Vi and Vj, what's the probability that the E becomes a crossing edge? Is what? Out of all 2t plus 1 choose t choices of I, you have to make sure that this I is in I and j is not in I, or j is in I and I is not in I. So we have I and j, and then either this happens, the capital I includes small I but not j, or this happens, it includes j but not small I. So what's the probability of this happen? It's actually this. So, because, we have 2 cases, either this case or this case, whether I will include I or j. So t minus 1 here. So if I includes I, then what we have to do? We have to choose t minus 1 elements, remaining elements of I. But we choose this from 2t minus 1, 2t plus 1, except I and j, because we are not allowing j to be included in this capital I. So out of 2t minus 1 elements, we have to choose t minus 1. And then ij roll swapped, then we multiply by 2. So using that, we can actually consider the expectation of x, which is summation of all probability that E is crossing. Because again, we can define xe be the indicator random variable whether E is crossing. Then this is same as probability that E is crossing. And we use the linearity of expectation. Then this is m times 2t plus 1 choose t, 2 times 2t minus 1 choose t minus 1. With some computation, we can actually prove this. You see that this is a bit bigger than half m. But so far we have done this, but we don't actually know the chromatic number of G. This is just assumption. We don't even know what T is. So we get actually boost, but that boost depends on this T, which we don't know. We want to write this T in terms of M. We want our final answer in form of the own expression as a M. But we know that there is also a relationship between M and T. For example, if M is large and choose 2, then T cannot be small. T is N, because this means it is complete graph, so N T is high. So if M is high, T must be high. So there are some relationship. And can we find the upper bound of T in terms of M, because this is M over 2 plus M over 4T minus plus 2, and we want to show that this is at least something. So to minimize this, we want to find the upper bound of T in terms of M. So T is some expression in terms of M. But if you have optimal coloring, V1, V2, V3, V4, V2T plus 1, there must be an edge between every pair. Because if there are no edges between these two, then we can take them together into a one independent set. Then we get a coloring with one less color. So this contradicts to the assumption that the original coloring was optimal. So we have this bounds. So number of edges must be at least 2t plus 1 choose 2. Because there are 2t plus 1 independent set, and between every two independent set, there should be at least one edge in an optimal coloring, if we take an optimal coloring. So how does that say? This say 2t plus 1 times 2t, 4t squared minus plus 2t. So in other words, this is minus 2m is negative. So 2t squared plus t minus m is negative, or non-positive. This actually implies that t is at most 4 under minus 1 plus square root of 8m plus 1. So this is just quadratic equation, so you can solve it. Then we know that this holds. And this is minimized when t is as large as possible. So this is 8m plus 1 over m. And if you multiply on both sides, same thing, square root of 8m plus 1 minus 1, square root of 8m plus 1 minus 1. Then what we get is m over 2 plus minus 1 plus square root of 8m minus 1, plus 1 over 8. So this is what we wanted. If the chromatic number is even, then you can carry out the same computation. And you can also show that the desired bound, even a slightly better bound, you can actually check that this is plus 1 in that case. So this shows a problem on max cut. So as I mentioned, this theorem is sharp. When n is say 2t plus 1 choose 2 m, then this is sharp. But what if m is not this form? Is it still sharp? So Eredish asked that is there infinitely many numbers? So this infinite sequence where any MIH graph has max cut of size more than this number. Where this goes to infinity as mi goes to infinity. So what it means is that on here this is sharp, and if you are slightly away, then you can again do some computation. Then if it is slightly away, then it's all the lower bound becomes the number of max cut is slightly higher, could be slightly higher than that, but not much. But if you are quite far from this number, so arbitrary number, then we don't know. We don't know whether this is best possible. So this is certainly true, but we don't know whether we can do better, much better than that or not. So what Eredish asks is that is there infinitely many number so that for those number, for graphs with that many edges, we can actually do better than this, or if this is not true, then this is essentially sharp for most of the numbers, most of the m. And in 1996, Alone actually proved this. The answer is yes. With this f being big omega of x to the 1/4, and prove that this is sharp as you cannot find the you cannot prove the same thing with the function which is growing much faster than x to the 1/4. And still, there are some research going on this direction. For example, what we can do is that if we forbid certain structure in the graph, then can we actually get a better max cut, larger max cut? So Alone proved that if G is triangle free, with m edges, then it has a cut width, the max cut width, at least m over 2 plus big omega of m to the 4/5 edges. So for general graph, it's as here, m over 2 plus square root of m. So this is big O of m to the 1/2. But if this is triangle free, alone show that we can actually get more. And this is best possible. And also he showed that there exists a triangle free graph with m edges such that every cut has size m most m over 2 plus big O m to the 4/5. So this exponent 4/5 is best possible. And some more results are known for F-free graph. So instead of triangle, if we replace with F-free, then what would we know? I mean, for some H it is known, but essentially not much is known. So yeah, this was one example. So max cut problem is one of the easy example of how we use the linearity of expectation. And let's consider one more example in the next video.